still going to do everything.
Okay, I was going to say, what's the definition of a logarithm to start with?
Is it on there?
Explain.
Oh, really?
Yeah, no, they're just like logarithms. Here's how you do this. I'm like, I don't even know what
What is a
Should we close the
logarithm?
door?
Are you sure you watched both parts?
I did watch both parts.
Alright, so by definition, the logarithm is the inverse of an exponential function. So, I don't know if you remember, but like, before we left for break in chapter 6, we learned about what inverses were. So the inverse of a function is what you get when you take the function and then you reflect it across the line y equals x. So if you take all the points on the blue exponential function and you reflect each of them across the line y equals x, you get this red function. That red function is a logarithm, or a logarithmic function. Okay, so that's what a logarithm is. Basically like an exponential thing, reverse. So it still has exponential-like behavior, just kind of backwards.
So it just flips over.
Backwards.
So if you listen to the words that are about to come out of my mouth, I'm going to wait for you to stop writing and then I'll say something else. Because I need to like grasp what I'm saying. Braden is ready. Alright, so with an exponential function, the x increases and then the y increases a lot, right? Exponentially. With a logarithmic function, it does it backwards. So as the y increases a little, the x increases a lot. Alright, or when we had decay. So with decay, as the x increases, the y decreased a lot, exponentially. So with a logarithm, they can do that as well. So I don't have a decay one graph, but I'll just kind of graph on top of this.
Should I copy down that little?
The graph?
Yeah.
Okay.
Or like an
Yeah, it's good to have. So decay would look something like this. Hold on. Probably more like
These are gonna be really ugly.
this. And so one thing that's kind of interesting about the inverses is with exponential growth and decay functions, you usually have that y-intercept 0, 1, unless it's, translated up or down or something. And so with logarithmic functions, you have the inverse of that point, which is 1, 0. So the inverse of this blue curve would go through the point 1, 0. And then the rest of the points reflect. So, for example, let's say, so I'm going to give this a name. Let's say that blue function is 1/2 to the x. Okay, so that's just like a regular standard decay function. We know a few points. We know 0, 1 is our y-intercept. We also know, like, if we raise 1/2 to the 1 power, we get a half. To the second power, we get a fourth. Here we get 2 and 4. So let's see if I can. So like -2, 4, right?
Okay, why is that so perfectly on that line?
Because I'm so good.
That was like crazy.
So that means that the inverse of that blue function, which would be a logarithmic function, would have the reverse points. So these would be switched. So you'd have a point at 4, -2, you'd have a point at 2, -1, 1, 0, 1/2, 1, and then 1/4, 2. So for example, you'd have a point at 4, -2, you'd have a point at
2 and 1.
1/4, 2, which is like here-ish. Let's see, 1/2, 1, what did I miss? 2, -1, so something like this. Okay? Inverse.
How is that inverse? It looks the same to me.
Then the blue one.
Yeah, I know.
Don't look at these two.
Yeah, I know. I am looking at the blue one. They're crossing over each other. I thought it would like flip upside down.
Well, I guess the decay one's different because so if you look at the tail, right? Look at the tail of the blue. The tail of the blue is going towards the asymptote y equals 0. The tail of the red is going towards the asymptote x equals 0.
Oh, so
So
it
the
just
tails
rotated.
are backwards, like the asymptotes are also inverses. So with Exponential functions, your asymptotes are always horizontal. It's like y equals 0 or y equals
Oh,
k.
it's just vertical.
Yeah, and so then with logarithmic functions, your asymptotes are always vertical. So like x equals 0 or x equals h, sort of. Like, not really h. They have their own. I don't know if we graph today. We might graph tomorrow. I don't remember.
They don't look hard to graph. They just like look.
So to graph them, you can basically
you just flip everything.
So I'm getting here. To graph them, you can rewrite it into an exponential form, and then it's like super easy to graph. So this is the definition of a logarithm, like technically in symbols or in writing. Every logarithm is going to have a certain base, okay? Just like every exponential function has a base. When we graph something like y equals 2 to the x versus y equals 4 to the x, these don't really look too different, right? They still have the same general shape, but this one, the points are a little bit farther apart because 4 is bigger than 2. If it was like 14 to the x, again, they still look the same general shape, but this one increases a little bit faster because of the 14. When you do like 14 squared, you get a really, really big number as opposed to like 2 squared, which is kind of slightly bigger. It's bigger, but small. So every logarithm has a base. I'm going to call that b, and it's similar to the base that we would have of a exponent. Then you're going to have a number and it's written as a subscript. Then you're going to have a number like sort of in front of that, not subscripted. So regular text. You know what I mean by subscript?
No. Oh, the guy on the bottom.
Yeah, guy on the bottom. Like
Yeah.
superscript, think exponent. Subscript, think like the opposite
That's
of
like
an exponent.
chemistry.
Yeah, so you're going to have a logarithm. So the red one here was a log with a base 10.
How do you know the base is good?
It's really tiny.
He's in there?
It's actually not in there, and I'm getting to that point, but this was 10 to the x, so I know that the inverse of it is going to have a log with that same base, but I think further ahead I talk about this. If you don't see a base,
Is it 1?
it's automatically 10.
Oh, it's automatically.
So if it just says log x, the default base is 10. So think everything we do is in base 10 because we have like 10 fingers, we have 10 toes. So when we do our decimal, like 0.1 is 0.10, like everything we do is base 10. So even our logarithms are in base 10. If you're using your calculator and you just hit log, which is like a blue feature, it'll automatically default to base 10 if you leave the little blank space.
Can you change it from?
Yeah, you can. You can change the base. Okay, so every logarithm has a subscript, that's the base. So that's basically what is telling you the relationship between x and y, if you're thinking graphically. So it's telling you how the x and y change with respect to each other. So with an exponential function, like y equals 2 to the x, the 2 is telling you how the y's are changing as we increase the x's. That's basically what a base is doing for a logarithm, just with reverse kind of activity. Because remember, like I said, as y increases a little, x is going to increase a lot, as opposed to with exponential functions, as the x increases a little, the y usually increases a lot. That's the exponential part. So the y's are increasing exponentially here, whereas over here the x's are increasing exponentially. Yeah.
So like an inverse example of exponential and logarithm would be like y equals log 10 and then x, and then like the exponential would be like x equals 10 something to the y.
10 to the
y.
x.
It's
So
y.
yeah, so an exponential function that would be the inverse of this guy would be y equals 10 to the x. But what we can do is we can rewrite this as an exponential function so that we can more easily identify what the numbers are doing. So when you look at this, you don't know what this means, right? Like, I have no clue what that means.
Is it like
And
1/10 or something?
Yeah, no, like, yeah, it's
Like,
like,
just like flip it upside down again.
exactly, and so that's why we have this definition. So what this means is, if we take 10 and we raise it to the y power, we will get x's. Which if you look at this and this, do you see how the x and the y are literally just switched? Like x is in y's place and y is in x place?
Yes.
Well, that's the definition of an inverse.
How do you plug in a y? Oh, you just
can.
choose y's.
So that's what we would do. So let's say it says, you know, graph y equals log base 10 of x. What we would do is we would convert it into its exponential form, which is this. And then when we make a table, instead of choosing x values, we would choose y values. Like that.
Ew.
It's weird. So if we, for example, plug in -2, so we'd have 10 to the -2 power, that's 100th. 1/100th. -1, that would be 1/10. 0, 10 to the 0 power is 1. 10 to the 1 power is 10, and 10 squared is 100. And so it would be backwards of what we were kind of used to graphing. So this first point is at 1/100th, comma, -2, which is like right here, and then -2 is like here. Okay, a 10th, comma, -1. 1, 0, which is right here. 10, comma, 1, which is off the graph, but it's like somewhere over here. See how we get that function? It's going to keep going, and it's going to approach the asymptote.
If we just like we can
X
graph
equals
those
0.
small ones,
Yeah, well, you
and
know,
you like will those count like when like a lot on
Yeah.
or something? You can
Yeah,
graph
yeah.
those small ones because they're gonna be fractions.
they won't be. So like I was saying before, the asymptotes will be reversed. You're going to have vertical asymptotes for logarithmic functions. It'll be something like x equals 0. If we put stuff in here, we might get more kind of shifts left, right, up, and down, but we're not going to do that right now. Basically what I need you to be able to do is, and we're going to work on this, converting it from logarithmic form to exponential form. Now they're equivalent things. We just write them in different ways. This way is helpful because we kind of know what that means. But this way is how we do math. Because you can't really do math with this because it's a y, but it explains to us the relationship between all the numbers. So essentially what you're going to do, you're going to take the base of the logarithm and you're going to turn it into the base of the exponent to rewrite it. And then whatever it's equal to will be the exponent. And the number next to the logarithm is what it will become equal to. Okay, so that's how you're going to rewrite the logarithm in its exponential form. And we'll go the other way too. We're going to take something that's an exponential form and we'll write it as a logarithm. And when we do that a few times, I think it'll make more sense what a logarithm actually is, because you'll see how the numbers relate to each other. So we're going to rewrite that really big over here. What did I make this, x or y? I forgot already.
It was an X.
X, okay. You might see this with different letters. The letters aren't important, it's the relationship that's important. So if you see it with like maybe a C or an A, or it doesn't matter. All right, so ignore the 4 for a second. The log with a base of 3 of 81 is a number. So this piece right here is something that you can type in your calculator and it's representing a number. So I want you to do that. So turn your calculator on and practice doing that. So turn your calculator on and you're gonna hit Control, and then there's a button that says 10 to the x. Right above it, it says log. So hit Control and then the 10 to
Oh,
the
it
x
literally
button.
is the number that equals right there.
Yeah.
I was like trying to think. I was like,
It's gonna come up with like some little blank boxes like this. Okay. In the little baby box that's a subscript, put 3, and in the bigger box you're gonna put 81. So log base 3 of 81, and then hit enter. What does it say?
4.
It says it's 4. Now, if you don't have a calculator like this, and it just says log base 3 of 81, you can evaluate that either using a calculator or using your brain, okay, because it has a value. Well, all we're doing right now is we're rewriting it in exponential form. So, okay, so what we're going to do first is take the base of the logarithm, which is the subscript, and we're going to turn that into the base of the exponent. Oops. All right, so then we're going to take what it's equal to, which is 4, and that is going to become the exponent. And all of that will be equal to the log number,
Which is 81.
81. Now, does this make sense? Is 3 to the 4th 81?
Yes.
Yeah.
Yes. Okay, so
You just said yes or no.
both of, well, all we're doing, it says convert each logarithmic equation, which is this, into an into exponential form. So all we're doing is we're rewriting this into an exponential equation. And when you look at it in its exponential equation, it's showing us a relationship that we actually understand. We know that 3 to the 4th, or 1, 2, 3, 4, 3's multiplied together is going to give us 81. So now, ultimately, what you need to know is that a logarithm, the base of 3 of 81, is going to give us the number 4. Okay, and you're going to figure that out by going back and forth. All right, so let's look at the second one. So the second one, where is this? We have the base of the logarithm is 5. So I'm going to rewrite this in exponential form by doing 5 as the base of my exponent. It says that log base 5 of x is 2. The 2 is going to become my exponent. And all of this is equal to x. Now, if we were trying to solve for x, what is x?
25.
Exactly. X is going to be 25 because 5 squared is x. So if you have something like this, there's no way to evaluate that as it sits. If it's an equation, we can solve it. If you have numbers plugged in for both, you can evaluate it. Okay? If there's an x in the log spot, then all you can do is solve it. Okay? So in some situations, we'll be using the conversion technique to solve. In other situations, we'll be using to just evaluate. Okay. Let's look at the last one. So you try. See if you can see the exponent. So 4 is going to be the base of my exponent. What will be the actual exponent?
1/2.
1/2 is going to be the exponent. And then all of this will be equal to A. Okay, so if we wanted to figure out what A is, we need to know what 4 to the 1/2 is, which you could type in on your calculator, or you could use your intelligences from previous chapters. Remember, anything to the 1/2 power is a square root. So 4 to the 1/2 power is the square root of 4. So what's the square root of 4?
2.
2. Okay, so this means that log base 4 of 2 is 2, because 4 squared is 2. All right, so just kind of like an in general thing. So if you see a logarithm, let's see. So if you see a logarithm, like both numbers are filled out like this, and you're trying to evaluate it. If the base is like smaller than this number, then you're probably looking at like a whole number, like 2, 3, 4, 5, 6, 7, 8. If it's reverse, if the base is smaller, or I'm sorry, the base is bigger, then when you evaluate, you'll either get a fraction or a negative number. So if the base is a bigger number, then that means that this evaluated is either going to be a fraction or a negative. That's like how that'll work. Now with that in mind, logarithms, like exponential functions, have restrictions. Yes?
Why is the right number a 2?
What's the right number of 2? This is what we had. Oh, I'm sorry. I'm missing, like, it's a 1/2.
confused.
Yeah, I don't know. I just like forgot the yeah.
I'm not sure. My legs just.
One.
Alright.
My face.
No, that's good.
I can like it feels.
If you remember when we graphed exponential functions, we had a domain of all real numbers, right? But the range was always not that. It was like y is greater than this or y is less than this. With logarithmic functions, it's the opposite. Okay, so your domain is not going to be all real numbers. Your domain is going to be restricted to, so if you're looking at like this, like a log base b of x, x has to be greater than 0. So this means that you can't take the log of negative numbers and you can't take the log of 0. So on your calculator, go ahead and try it. Type in like log base 10 of 0. Type in log base 10 of like negative 2 and see what it says.
You know how many times I've been
So
so
it's-
confident?
It's sort of like square rooting a negative number, or it's like dividing by 0. You can't do it.
I have a log thing, but what would it, does it look, I don't know if you know how to use these, but I have like a log
It's not a
thing.
calculator.
But do I do like that?
Your log, that calculator only does log base 10.
Non-real
Oh, it does?
calculation.
So
Oh, so I just do have to do log, I just do log and then the parentheses, I just put the name, the
negative
number?
2 or 0. Yeah.
Okay.
I'll do them after school with you.
Yeah, if you're using a calculator that is not this calculator, okay, that's why we require this calculator, Kathleen. The reason we require this calculator is that it allows you to do other bases. Every other calculator that is underneath this grade of technology will only do base 10.
It's upsetting.
How many bases are there?
So many.
Infinitely many.
It said there was like, it
So-
said it was an algebra 2, thing.
It is, but you would have to, every single time you do math, use a change of base formula if you aren't using base 10, and we're not gonna use base 10 the whole time. In fact, we rarely use base 10. So that's why this calculator is the required calculator, because it allows you to easily compute logarithms with different bases, whereas every other calculator, including your phone, is only gonna do a log with a base 10.
Can I cheat the system and kind of like make it to where it answers?
Yeah,
for
you
me?
can, but I'm not gonna teach it unless you come for extra help.
Okay, then I will.
Okay,
Oh, I
so
found
let's
it.
go the other way. So now we're gonna take something that's in exponential form
I found it.
and rewrite it in its logarithmic form. So
Ooh.
going backwards. This is an exponential equation, and the exponential equation has a base of 10. So that base of 10 is now going to become the base of my logarithm.
I have a log with like this thing, look. See it? It has like the smaller thing and then the
Sure.
taller thing, yeah.
The exponent is a 3. Now where does the 3 go, left or right?
Right, sorry.
Right.
I forgot which way is left and right.
And then the 1000, what it's equal to,
It's raised to the 1000.
is right here. Well, it's not raised.
It's just shown there.
It's on the same level. So log base 10 of 1000 is 3
Mine looks
because
like it's
10
like 8-0.
cubed is 1000. Okay. So again, if you were to type this in on your calculator, like log base 10 of 1000, it would tell you it's 3. So this has a value. Just like if you type in 10 cubed on your calculator, it would tell you it's 1000. Something that you can evaluate. Now, here, if this is an equation, it's asking 5 to what power is 600? Now, do you know what exponent of 5 would give you 600?
Well,
20.
2. No, wait.
It's big. What's
Ooh.
5 squared?
12.
4.
5 squared is
Four. It's
25.
It's 4.
What's 5 to the third?
Oh wait,
125.
125.
What's 5 to the fourth?
600.
6.
625.
5 to the 6.
600.
Okay, so we're already above 600, so what is it?
Ah,
5 to the
this
6.
is a decimal.
4.5.
It's not a rational number, it's a
No.
decimal.
So,
So
So that's
Oh.
why we need
So the
logarithms.
answer is false.
No.
In order for us to solve this, we need a logarithm because it's not going to be an integer and we can't guess it. So we need to rewrite this in logarithmic form.
Log
That's like genius.
5 600
Yeah.
equals x.
So
Who
so we
created
have
logs?
I don't
God.
They must be
know
very
that
smart.
one, but I'll look it up for you.
Thanks.
All right, so we're going to take the log of the exponent and we're going to turn it into the log of the wait, what did I just say? The base of the exponent and we're going to turn it into the base of the logarithm.
But isn't the 600 on
The
the left
600
side?
is on the left side.
3.97.
Yeah, left.
Hey,
Now my left for my right.
I forgot
right
your 600. There you go. Oh,
Well, I
that
just wasn't done. I have to color code everything.
Oh, I'm sorry. I didn't mean to interrupt.
Yeah. Now, in order to solve this, you would then go to your calculator and you would type in this, and it would give you the answer, which will be an irrational number, okay?
4.9.
No,
4.64.
Which means you'll have to round.
What really annoys
Whoa.
me is how, like, if this is something that we do in, like, algebra all the time, like, why is it
Almost 4, like 0.03.
I got 3.97463586871.
9746, what comes after the 6?
3.
3.
Okay. So this is an approximation to the exponent that would that you would need if you wanted to know 5 to what power. That's the power that you raise 5 to in order to get 6.
So
I don't
what,
know.
for the
3,
decimals,
4,
do you even like?
we use different for different.
Do you want us to
That's the
round?
one at the end of like the equal, that's not even an equal sign. What is
That? That is an X.
Oh.
Yeah.
That would be an X.
That would be an X.
My bad.
No, my bad. I just got carried
Sorry,
away.
I just can't read
Like,
that.
what's a
Fish.
fish? Yeah, it's a fish. Like from last week. I'm assuming you're gonna do that.
Do I have to do them?
I mean,
We'll see what
you
she
should.
says.
We'll talk. We'll talk after class. Yeah, you do. All right, so in order to figure out what this is, 1,000 to some kind of power is going to give me a tenth. Now, I've been putting question mark, but if you want, you can go ahead and put like a variable there for you. It's up to you what you want to do, okay? Now, keep in mind that you can just plug this into a calculator and it'll do it for you. We're just practicing doing it without a calculator because, again, it's going to give you like a greater understanding about what a logarithm actually is. So, what this logarithm is equal to is 1,000 to some sort of power is going to give me 1/10. Now, if it's a fraction, okay, then that means it's going to be negative. And if the fraction is
smaller
like,
than-
yeah, like, so if like the butt of the fraction is even smaller than the number, then it's going to be
A
like
negative
a negative fraction, yeah. So
Oh.
if you ignore the fact that it says 1/10, if it's just 10, what would it be? Like 1,000 to what power is 10?
It'd be negative 3.
Oh wait, oh, yeah, the answer is that.
No, the answer is a negative 3.
So 1,000 to what power is 10?
Negative 3.
No, not 3.
Negative 1/3.
1/3.
Oh,
Yeah.
Okay.
Just 1/3. So
Yeah.
then
Just 1/3. So if we're looking at 1/10,
It's negative
be
1/3.
negative, yeah.
I like, because at first I wrote negative 3, and then I like plugged in to
So
check my
that's what
work,
this is equal
and it was like 1 over like 10,000. I was
to. Right, because it's gonna make the,
Yeah,
it's gonna make it bigger.
so I
Like
was
more
like, oh,
zeros.
that's
It's gonna
wrong.
add zeros. We want to take
Right.
away zeros.
I'm really confused as why you walked over here and then it logged me in on both websites. So
I bet you were in the wrong. You were on mathexcel.com instead of mathexcel.
No, because I was on Math Excel for school because it had that bookmark too. I was on the right website.
So maybe
just
it
like,
was a glitch and it's done.
I have
Being
no idea.
done now.
That's the weirdest thing.
All right, so I would say the most well-known application of logarithms is the Richter scale, which is used for measuring how unfortunate an earthquake is.
Nice.
So you know how like we live in Florida, we have hurricanes. We don't have earthquakes, but we have like Cat 1, 2, 3, 4, 5, 6, 7, and that 5. The end. Sorry, I just kept going. Yeah, so Cat 1 through 5. That's a linear scale. Like when you look at like a tropical storm to like a Cat 1 or Cat 1 to Cat 2, it's like a certain wind speed. It's like 10 miles per hour to 20 miles per hour, and the next one's like 21 miles per hour to 30 miles per hour, whatever. So those are like pretty easy to follow. With the Richter scale, which measures stuff that maybe you know nothing about because we live in Florida, you're measuring, or you're comparing two major things, the intensity and the magnitude. So the magnitude is like Cat 1. That's like the score, I guess, if you want to consider it, like the value that they are giving it based on like this scale. So if it says like magnitude 5, think category 3 hurricane. Like that's like their scale.
Would you like
The-
give us this on the quiz, like the Richter scale?
The Richter scale, yeah.
Yeah.
I'll give it to you. The intensity is, oh, what is that thing? Like that seismograph.
Oh, yeah.
That's measured with science that I'm not going to try to explain to you.
Don't even.
So not a science teacher, but a science teacher could probably explain it better to you. But the little thingy goes up and down, and like, you know, based on how sucky the earthquake is, it goes up and down more or less. So that's what intensity is. That's like an actual science thing, which again, I'd explain to you, but I think I'd explain it wrong, and I don't want to do that. So this is basically it looks exponential, okay? It's an exponential kind of graph explaining basically the difference between like a magnitude 5 and a magnitude 8. Do you see how drastically different it is? Because it's exponential.
The 1 and the 2s are like close.
This is 10 to the 5th versus 10 to the 8th. So that's the difference between a 1 with 5 zeros and a 1 with 8 zeros.
What is 6? What is the
Okay,
letter in
those
6?
are very different numbers as opposed to like 5 and 8. So technically, this this like graph is the exponential version of the logarithmic scale. So the log has no base, which means we know that it's of base 10. So essentially, if you take 10 and raise it to what they're calling the magnitude, you get the intensity of the earthquake.
Holy crap.
So there's a big difference between like a magnitude 5 and a magnitude 8, or even a 5 and a 6, or even look at the 7 and an 8, as opposed to our hurricanes. Like there's not really much difference between like a 2 and a 3, or a 3 and a 4. Like there's not much difference. There's a difference between a 3 and 5, but it's not as much of a jump. Yeah.
Oh, what is it? For 6, what does that word say?
So this says,
Moderate.
so
Oh,
down
moderate,
here it
okay.
says not felt. So a magnitude 1, 0 or 1 is not felt. Minor is 2 to 3, small is 4 to 5, moderate is like 5, 6, strong is 6 to 7, 7 to 8 is major, and then after 8 it's like
Does it go to 10?
catastrophic.
I think it goes up to 15.
Why is there a negative?
I think it just, I think the record awfulness
Was it 15?
still was, no, it's definitely not 15, it's like 8, 9.
Really?
That
No.
right
That's
there
why-
was,
Because there was an 11.
so
the
that
other-
was the record at the time, was like 9.3. It's gotten worse, like the one in Chile like a few years back was pretty bad, but 15's way too big.
Wait, I thought
It's
there
not gotten that far.
I'm gonna look
Yeah.
that up.
Why is there a negative?
I thought there
one?
was.
I'll believe 11.
What are you looking?
Where is
thought,
there a
like, the
negative
last one
1?
On the bottom.
Of what?
On the, like the.
This?
Oh, on the bottom of that graph, there's a negative 1. Where the arrow is.
Well, 10 to the negative 1 is a 10th, so I guess it could be
Is
that- it could be that
It
minor.
could be like the ones in California. We don't actually
should be
feel
really
anything, but they
minor,
happen.
like a
But
what do they
then
call
that'd
those?
be
Like
like,
the-
is that one?
the
or
little
is it-
shiver, I don't know. Alright, so what we're gonna do in this
Temblers.
example is we're gonna compare 2 earthquakes. So to compare 2 earthquakes, we use this, which is, like, we haven't learned logarithmic properties yet, but basically this is just, you're gonna use this. Write this down because it's on the homework, and the homework doesn't really give it to you. So make sure you have this somewhere. It's on the, like, help me solve this part of the homework, but
You have like 2 minutes.
I know, we can get through it. Alright, so in December 2004, an earthquake with magnitude 9.3 hit the northwest coast of Sumatra. In March, another earthquake came, but it was a magnitude 8.7, so like slightly less,
Oh,
but
these
still
aren't
pretty
that hard.
terrible. How many more times intense was the December earthquake compared to the March earthquake? So what we're gonna
Never
do
mind,
is,
you're
we're
right.
gonna use this. These are magnitude numbers. So we're gonna plug those in here. So the first one was 9.3, the second one was 8.7. And we're gonna compare the intensity of the first one with the intensity of the second one using a logarithm with a base of 10. Okay. What is 9.3 minus 8.7?
0.6?
Hmm?
0.6?
Yep, so I'm gonna rewrite this over here.
Someone
So
asked me to subtract.
a logarithm is equal to 0.6. Now that doesn't mean that the first earthquake was 0.6 times worse. That's not what that means, okay? In order to get the answer here, which is how many times worse the first one was compared to the second one, we're gonna rewrite this in exponential form.
How do you move the eyes or like?
We're just gonna leave them actually like that.
Oh.
But in order to do this, we need to know that our base is 10. So to rewrite this in exponential form, we're gonna take the base of the logarithm, which is 10 if it's not written, and we're gonna raise this to the 0.6 power, and that is gonna give us the answer, which is how many times worse the first one was compared to the second one. We're comparing intensities. So this quotient is what we're solving for. So all you're gonna do is just type this in on your calculator, and that's gonna give you how many times more intense the first one was compared to the second
Just
one.
10, 0.6.
10 to the 0.6.
Yeah.
Yep.
I got 3.98,
Yeah.
1071.
So, like about 4 times more intense. Ish.
We really don't do anything with the eyes. I feel like that looks so
I know, I
weird
feel like
that.
it'd be like the opposite way around. Like you had to find the I one over
We're
I2.
comparing one to the other. So the quotient is representing what you would multiply by to get the other one. If that makes sense. Like 4 times 2, it gives you 1. Like 4 times intensity 2 gives you intensity 1. That's what you're comparing the ratio of the intensities. We will pick up the graphing ones tomorrow and then do more log stuff.